Let's take a look at 3.6, polynomial and rational inequalities. So for inequalities, we're talking about less than, greater than, less than or equal to, or greater than or equal to types of stuff. So first, let's look at our past concepts. For example, let's take a look first at linear inequalities. And so linear were of the form ax plus b, and then you have an equal to 0 type of thing. But in this case, this will be an inequality, so we'll have one of those in there. So if you're asked to solve something like this, this is how you would have done it. So solve 4x plus 8 less than or equal to 0. So what you do is you solve or isolate x on one side. Solve or isolate the variable, in this case x, on one side. And it's usually easiest or best to do this on the left-hand side. And I'll show you why that can be an issue after we do this one. So first thing you do is isolate x. So you subtract 8. Subtract 8, divide by 4. Okay. So you get 4x less than or equal to negative 8. Divide by 4, x less than or equal to negative 2. And be careful on things, if this was negative and you divided, what would you have to do to the inequality? You'd have to flip it, or remember those sort of things. And then we would graph this on, it's just a single variable, so it's just the real number line that you graph. You label 0, and then you go to negative 2. And then do we include negative 2 or not? That's the question. And yes, we do include it. Because of the or equal to, you must include it. So what I like to do is put a dot. You can use dots or brackets, but I put a dot. And then it says the x values are less than negative 2. And so you would go this direction. And so what I want to show you is just the idea of a test value. So you go this way. You put your arrow like that. And so that's negative infinity to negative 2, and then you include it with a bracket. So some books, and sometimes you've seen this, where you would have seen it like this. And then you have to do a bracket and then go this way. So you could do that too. But I don't like to do the bracket because then I need to know the direction first. I like to figure out, do we include it or not? Put a dot or a circle, and then you look at direction. Now, let's suppose you had something like this. What if you had 5 greater than or equal to x? Then what would that graph look like? Okay, so you go to 5. We know you include it, right, because of the or equal to. So you include it like that. And then which direction do you go? And the best way to, so this is where you got to be careful. Do you go to the right or to the left? So 5 greater than x. So with the x on the right-hand side, we have to be careful. We do not just go direction. You have to think of what it's saying. So if the 5 is greater than, and if you think of this as like plural, x values, then you can see it has to be on the right side. So you go, let's go this way. So what we will do in the long run is we will choose a test value. And that test value we will choose, say here is like negative, well, let's actually choose 0. So if you choose 0, then you say 5 is greater than or equal to 0 is true. So you shade that direction. Okay. Hopefully this doesn't mess up our screen. We're going to go this way to get more on one page. I forgot I do that. All right, so at some point you just stop being picky about how these look and just do it. So, okay, that'll fit one page right there. That's how I've been doing it, I forgot. All right, so now let's look at a polynomial case. So for polynomials, let's let p of x be a polynomial. Function. And so we have polynomials. They do, they do their thing. They go like this or like that or whatever. So we have all those different cases, right? So we'll look at those polynomials. So we want to look at p of x, the polynomial being less than 0, greater than 0, less than or equal to 0, or greater than or equal to 0. We're looking at those 3 different cases. And for now, let's suppose we have a graph. So we know polynomials can be graphs. So if we think of it as just a graph, then we're going to get these different possibilities. So you have this and this, x and y. So you could have, let's suppose you have just a quadratic or something, and you could imagine a graph doing just something like this, of a quadratic. So that's my polynomial p of x. And let's say it crosses here at A and here at B. Then what values of x is it greater than 0? So we could ask, so if this is p of x, we could ask that question. We can say p of x greater than 0 for what values? Okay, so let's pick some values. All right, so greater than 0 means what? Well, means it's this direction above the x-axis. So remember, p of x is y. It's these values above the x-axis. So which values are above the x-axis? It's everything between what and what? It would be everything here. So your solution in this case would be a to b. Why do I not include a and b? Because it's just strict inequality. Okay, so we could go down the list of all these things. We could ask the question, p of x, let's just do less than or equal to 0. And we'll do them all. Seems kind of a lot to do them all, huh? So if it's less than or equal to 0, then what do you get? Well, less than 0 is below the x-axis, so it's those. And it would be all of these values and all of these values where you plot the graph and you get p of x less than 0. So you go down and over it like that. And then do you include the endpoints? In this case, yes, you would include those endpoints because of the or equal to. So in that case, we get this solution. So you get including those endpoints. So you put dots, and you go this way, to the left and to the right. So you would say negative infinity up to a, include it, and then you union including b, and then approach infinity, like that. Okay. Then we could talk about just some arbitrary graph. This is when it gets a little more complicated. So I could have a graph that does something like this. Let's suppose. And let's suppose this passes at x1, x2, and x3. All right, so we could ask, and let's just call this function, let's call it f of x. So that's my function f of x. then we could ask the same question. When is f of x, try that again. So when is f of x greater than 0, and when is f of x less than 0? And let's do or equal to. Well, let's just do strict inequalities, and if they're equal, you have to include the endpoints. Maybe let's do it like that. All right, so then go ahead and try that. Okay, so try this. Pause the video or whatever. Okay, and so less than 0, we are below the x-axis, so we're talking about these intervals. So it's to the left and in between. So I did that in the wrong order, didn't I? Let's do greater than 0 first. Okay, so greater than 0 is above and then above. So what you should have gotten. So what's the solution for that? Above would be x1 to x2 union, and then you're all the way there on x3, and then you approach infinity like that. Less than 0, negative infinity all the way to x1 union, below, and then it's x2 to x3. Okay, so that's what you should have gotten. Okay, and that's if you do not include the endpoints. If you include the endpoints, then you put brackets on the points. Of course, never on infinity, but on the points. Okay, let's continue. So now we will solve and look at these two possibilities. So we're going to do first by graphing a polynomial like this, because they're kind of simple to graph. We have to factor anyway, so we can easily factor it. And then we'll look into the other method, which is using test points. Okay, so let's take a look at this example. Okay, so go ahead and move this all the way up right now. Example, solve 2x times x minus 1 strictly less than 21 minus x. All right, so that's, may or may not be obvious it's a quadratic, but that's kind of how they start. So first thing you do is you basically get all the terms on one side. So you recognize this quadratic and you write as p of x, in this case, strictly less than 0. So I like to say in quotes, you get 0 on the right-hand side. So we do the process. We distribute x, or 2x, add x, subtract 21. Let's do that. So you're going to get 2x squared minus 2x less than 21 minus x, and then 2x squared minus x minus 21 strictly less than 0. Okay, so it's a quadratic, so you factor that. Okay, so if you factor it, product of two binomials, less than 0. It's got to be 2x and x. And then you do a little stuff off to the side if you want. 21 is 21 and 1. Oops, I wrote a 7 for some reason. 21 and 1, and or 3 and 7. And it looks like you want a difference to be 1. I'm sorry, not 1. Well, yeah, after you do the product, I'm sorry. And then you have 2 and 1. So you got 2 and 1 as well. And so you want to do the product, and then the difference is just 1. So it looks like 6 and 7. That's got to be it, right? So 2 times 3, and then 7 has to be it. So this has to be a 3. and this is 7. And you want the larger product to be negative. So that means this is negative and this is positive. All right, so then set each factor equal to 0 and solve. So set each factor equal to 0 and solve. So you get 2x minus 7 equal to 0, or x plus 3 equal to 0. 2x is equal to 7, x is equal to 7 halves, or x is equal to negative 3. All right, so here's the deal. These are called critical values. So the 7 halves and the 3 are called critical values. So another statement where, this is kind of in quotes, I guess, but where each factor is 0 is called a critical value. And there's a reason we call it a critical value, or sometimes just CVs. So here's the question. Are 2/7 and negative 3 solutions to this? That's your question. Are they solutions? And the answer is no. How come? Why are they not solutions? It's because this is a strict inequality and not or equal to. So they're not solutions, but that's the pivot point around 0 is what's happening. So if we look at the function like this, f of x equal to 2x squared minus x minus 21, and you know it factors to that, 2x minus 7, x plus 3, those are zeros of the polynomial, but not the inequality. They're critical values. So we want f of x to be, we want f of x to be this thing, to be less than 0. So let's graph this thing and see which values are less than 0. Okay, so we go to 7 halves, so that's up here. Just, you don't have to label it, just put a dot. And negative 3, 7 halves, and we're not going to include those. The y-intercept is negative 21, is way down here. So the graph, how does the graph open? Is actually my question. So the graph, so 2 is greater than 0, so it opens up. And the intercept is way down at negative 21. So we know the graph looks approximately like this if we were to graph it in 2 dimensions. And so what part of the graph is below the axis? What part of it is above the axis? And so we are interested in f of x being what? Less than 0 or negative. So negative is these values. It's below. So from here you can just look at that and graph it. So the solution set is not including negative 3 to 7 halves. Not including 7 halves for the same reasoning. All right, so that's one way to do the graph the polynomial and solve this inequality. Is you literally just graph the function and just see when the graph is whatever it's asking, above or below the axis. Okay, the next way to do this is called is using a sign chart. Okay, so we're going to use. I'm going to show you the sign chart method. Okay, sign chart method looks like this. So you first plot critical values. Okay, on the number line. Okay, so here's our number line. Draw it kind of big. And you plot your critical values, -3. You always want to label 0, and then plot 7 halves. Now, we already know we're not going to include those. You put circles around those. And then what you do is you draw a dotted line, and I would below it. This is just basically just separating your intervals. This is just kind of a chart to there. Okay. And then to the side, write down your factors. So our factors are over here, 2x minus 7 and x plus 3. Okay, then what you do is you choose, I'll do it right here, I guess. So choose what we call test values inside each interval. Because the critical values break this up into intervals like that. There's 3 different intervals. So you go through and you choose a test value inside the interval. So here's -3. So you choose anything to the left of -3. So you could choose -4, -5, whatever. So let's just choose -4. I often like to choose like -10, like way out here, to make it simple. And then you substitute -4 inside the factor and determine the sign, whether it's plus or minus. Okay, so let's do that. So you put -4 in, multiply, you get -8, subtract, so that's a negative. Okay, and then you do the same thing for x plus 3, and you get a negative. Now, test value in between, choose 0, substitute in, right? So you're literally substituting in 0 into here. You get -7, which is negative. And then putting in 0 plus 3 is positive. Okay, so it's positive. And then choose a test value out here. Let's just pick a large one like 10. Substitute in. So if you do 10, you don't have to actually show all those steps. That's pretty clear. That's positive. You don't have to really do the calculation. Okay, and then same thing for the other one. 10 plus 3 is positive. So everything's positive out here. It's pretty obvious. We put in a large number. And then down here is the product. So the product, all you really do is count signs. So even negatives, positive. Odd negatives, negative. That's all you're doing. So 1, 2 means this is positive. 1 means this is negative. 2 positives is a positive. And what are we interested in again? We're interested in, it was p of x. We wanted it to be, actually we used f of x, but whatever, to be less than 0. So we wanted in other words, the product to be less than 0, which of course is everything in between. And so then, that's it. You state that interval, not including the endpoints because it's a strict inequality. -3 to 7 halves. And that's the basic sign chart 1. We will do a couple more after this. We'll do probably one more video and get to rational inequalities as well.